Hello, welcome to this video where we continue with seasonal inventory management. So in this video, we'll talk about the ideas of fill rate and cycle service levels, demand service level, and so on. So that's the idea for this video. So let's begin with the idea of fill rate. So in the previous video, we looked at the example of the LL Bean example, and then we found that the optimal order quantity is 1300. So when you order 1300, that is when you make the most profit. For all the other order quantities, your profit will be lower, right? So we look at a systematic way of figuring that out instead of having to try many values. But first, what if you do order 1300 items, then what is your fill rate? So how often will you be able to fill demand, right? So that's what we want to find out. So let's go back to this Excel sheet that we were looking at. So we'll say fill rate for 1300. Now we'll do it for 1300 because 1300 is the optimal order quantity. So 1300 gives you a profit of 54,160, expected profit of 54,160. If you order 1000 or 1100 or more than 1300, say 1400 or some other number, your expected profit values will be lower. So 1300 is the optimal value. So what is the fill rate for 1300? Now, what you're saying is that if I order 1300 items, then as long as demand is less than or equal to 1300 items in all of these scenarios, we will be able to fill 100% of customer orders. But if demand is more than 1300, we can only fill a certain percentage of customer orders, and that's what we have to figure out. So for all of these scenarios, the fill rate will be 100%. It's 100% all the way till the case when demand is 1300. So starting when demand is 1400, you won't be able to fill all your orders. So what percentage of orders can you fill when demand is 1400? So when demand is 1400, you ordered 1300 items, but demand is 1400. So you can fill about 92% of. So let me make that, yeah, let's make it all percentages, right? Let's make them all percentages. Let's do a couple of decimal places. Now for these, I don't want that. Right? So it's 90, so you can fill 92.86% of demand when demand is 1400. And when demand is 1500, you can fill 86.67%. 81.25% when demand is 16. When demand is 1700, you can fill only 76.47%. So that's the worst case scenario. So the worst case scenario, you'll only fill 76.47%. So what is the fill rate? Or the expected fill rate, I'm sorry. So the expected fill rate is, again, we'll do the same thing. We'll multiply the fill rates with the corresponding probability values and add them all up. So some product of the fill rates for the individual scenarios times the corresponding probability values, and there you go. 99.02. So you know what? I don't feel like decimal places today. Let's get rid of them. Just so fill rate is 99%. So on an average, you'll be able to fill demand 99% of the time. Now there is a 1% chance that you'll only be able to fill 76% demand, or there's a 1% chance of 81, but for a very large portion, you'll be able to fill 100% of demand. So the average works out to be about 99%, right? So that's fill rate. So that's basically what how we calculate fill rate, and that's the idea behind fill rate. Okay, so if you ordered only 1000 items, the fill rate will be lower. So what you do is you'd make it 100% up to 1000, and then from that point onwards, fill rates will be less than that. So it'll be 1100. So it'll be 1000 divided by 1100, 1000 divided by 1200, 1000 divided by 1300, and so on. So you'll calculate the fill rates, and then you'll calculate the expected fill rate, which will be lower, right? So I'll leave that calculation to you. Now,
Is there a better way of figuring out that ordering 1300 it gives you the highest profit, right? To do that, what we'll do is we'll calculate those two costs that we talked about before, which is the cost of understocking and cost of overstocking. Cost of, let's begin with overstocking. And the cost of understocking, right? So what is the cost that you incur if you had one extra parka, right? So that's the cost of overstocking. So if you had one extra parka, it means that you made the parka for $45 and you can only sell it for $40, which means that you've lost $5 of profit, and that's the cost of overstocking. The cost of overstocking is the difference between the uh, price of the value minus the salvage value, because salvage will always be less than the cost of making it. The cost of overstocking is $5. Now, what is the cost of understocking? Cost of understocking is what happens if you have one fewer parka than demand, right? So if demand is 1001 units and you only have 1000 units, then how much money have you lost? Well, so if you have one fewer parka, you have essentially lost out on making a single sale or making $55 of profit on that one single sale. So cost of understocking is the profit for a single unit. So you could have sold it for $100, made it for $45, and made a profit of $55. So cost of understocking is 55, and the cost of overstocking is $5. So it is much better to be overstocking than to understock, right? So that is why even though average demand is 1026, the optimal order quantity is 1300. It is much more than the average because it makes more sense to overstock than to understock. So you have to do one or the other. It is impossible for you to exactly predict what demand is going to be for a season. If you do that, that's a fluke. So because you're either going to be understocking or overstocking, which way would you lean? Well, that depends upon the relative values of these costs. So cost of overstocking is only $5, but cost of understocking is $55. It makes more sense to overstock, and that is why the optimal order quantity for the season is 1300, right? So how do you figure that out? So to do this, what you do is we calculate something called the cycle service level. So what is the optimal cycle service level? So we calculate the cycle service level. The formula for that is straightforward. So cost of understocking is represented as CU, and the cost of overstocking is represented as CO, right? CO for overstocking, CU for cost of, oh, I'm sorry, it's the other way around, cost of overstocking and the cost of understocking. Now, the cycle service level is calculated using a formula uh, which is CU divided by CU plus CO. Like I said, it is based upon the relative values of CU and CO. So if you add up the values of CU and CO, what percentage of that is represented by the cost of understocking? That is what the cycle service level is calculating. So it is CU divided by CU plus CO. So I can calculate that. So that will be CU divided by CU plus CO, right? Which is 91.6667. So let me 2 minute decimal places. Let me bring that down to 2, right? Actually, let's make it 4. Now, how do I figure out that my optimal order quantity is 1300 given that my cycle service level is 91.67? So your cycle service level is 91.67%, which means that you will be able to satisfy about 91.67% of customer demand. So given all the different scenarios and probabilities that you have, optimally you should be able to satisfy 91.67% of customer demand, right? So how do I figure out what my order quantity should be so that I'm able to satisfy this? To do that, what we'll do is we'll take these probability values, right? And then we'll calculate the cumulative probability. calculate the cumulative probability. Cumulative probability is the probability up to that point. So for example, cumulative probability for this will be 1%. The cumulative probability for 500 will be, what is the probability of being 500 or lower? There'll be 2% plus 1%, right? 2% plus 1%. That'll be 3%. What is the probability? So cumulative probability for 600 is the probability of being 600 or lower. And that's the sum of these three numbers. So each time we are adding an extra row. So what is the probability of being up to that number, up to that number? So by the time you come to the end for 1700, you're adding up all of these probabilities, which should add up to 1, right? 100%. So how do I write a simple formula for this? There's a simple way to cheese this. So this is, it says the sum of all numbers. You'll always start here, right? So the starting point is always here. So I'm going to make that an absolute reference. But the ending point is different. So I'm going to start with the same ending point, but notice that this time I don't have a dollar sign. So by this I'm saying that I'm always going to start this sum from the first row, but I'm going to end it at different rows, right? So for the first one, I'm going to end it at the first row. For the second one, I'm going to end it at the second row. It's going to add the first two numbers. So if I bring it down and if I copy it down again, now it's going to add the first three rows. And if I bring it down again, so if you'll notice the formula, the difference is it's always starting at B2 because we put dollar signs here. But as you copy the formula, the place where it ends increases. So this is a simple way of making sure that if you're adding things that always start at a particular point and increases in the column, this is how you do it. You'd put dollar signs for the first one, but not the remaining. So you can do this for the whole thing here, right? So these are my cumulative probability values, right? So this tells me that the probability that demand is 1000 or lower is 51%. Probability the demand is 1100 or lower is 71%, and so on. So how do I figure out that 1300 is my optimal order quantity? Well, look at the cycle service level and then find the first time the cumulative probability becomes bigger than that number. So this is 91.67%. The first time the cumulative probability value becomes bigger than 91.67% is 0.92, which means that 1300 is your optimal order quantity. It's as straightforward as that. You don't have to go through all of these calculations where you do them one by one. Instead, you calculate the cycle service level and then you look up the cumulative probability values and find the first time the cumulative probability becomes bigger than this, and then that gives you the optimal order quantity. So that's the idea behind how you calculate the optimal order quantity for a discrete distribution, right? So optimal order quantity is 1300, fill rate is 9900, the expected profit for this scenario is 54,160, and that's basically it. So that's the scenario here. So given this demand distribution and given this cost structure, the optimal order quantity for LL Bean for this season, they should manufacture 1300 parkas. They will be able to make an average profit of $54,160. They will have a service level of about 91.67%, and they'll have a fill rate of 99%. That's that particular scenario, right? Okay, so in this case, so what we'll do is we'll look at another example where the distribution is not a discrete distribution, but a continuous distribution. We'll use a normal distribution in this case. We'll see how things differ, and then, yeah, so, and then we'll take it from there, right? Take care.